let's look at some rules with regards to assigning oxidation numbers. Now, oxidation numbers are simply a way of keeping track of how many electrons are gained, how many electrons are lost, and by whom. So, in order to understand oxidation-reduction reactions, we have to be able to assign these oxidation numbers. So, to start off with, elements always have an oxidation number of 0. If they have no charge and they're by themselves, they have a 0 oxidation number. The sum of the oxidation numbers of compounds is also going to be 0. And then if you have a polyatomic ion, the sum of its oxidation numbers is simply going to be the sum of the charge of that polyatomic ion. Now, oxygen normally has a -2 oxidation number, except when it acts as a peroxide, O2. In that case, it has a -1 oxidation number. Now, hydrogen has a +1 oxidation number, except when it's bound to a metal, like for example, in the example of sodium hydride that we saw before. In that case, because sodium has a +1 oxidation number, which we'll get to in 1 second, hydrogen, the hydride ion, would have a -1 oxidation number. Fluorine is always -1, and while halogens tend to have an oxidation number of -1, they can actually have variable oxidation states. Group 1 metals always have a +1, and group 2 metals always have a +2 oxidation number. And positive charge generally comes before the negative charge. So keeping all of this in mind, if you see oxygen, normally -2 for the most part. Hydrogen normally +1 unless it's a hydride. Fluorine always -1. Other halogens you can't 100% of the time tell, but they tend to be -1. Group 1 metals +1, group 2 metals +2 oxidation number. So let's look at in practice too. I've got potassium permanganate here. The first thing I look at always is oxygen. Oxygen is always -2 unless it's a peroxide. And potassium next because it's always +1. So now I need to determine the oxidation number of manganese. Well, that entire compound needs an oxidation number of 0 overall. Well, oxygen is -2, but there are 4 of them, so that's a total of -8. Potassium has a +1, so in order for the overall oxidation number to be 0, manganese must have a +7 oxidation number. Okay. For the next one, oxygen is always -2 again, and if you look at that, that means that the total oxidation number contributed by oxygen is -8. Well, here's a problem. This is a polyatomic ion with a 2- charge, meaning the overall oxidation number needs to be -2, which means since oxygen is overall -8, sulfur must be +6 in order to have an oxidation number of -2 for the entire polyatomic ion.
So now that you've learned how to determine oxidation numbers, we're going to be talking about redox reactions. So in a reduction-oxidation reaction, what happens is that the element that is being oxidized is going to donate an electron to the element that is being reduced. So the way that you know that a reaction is a redox reaction is that the oxidation numbers of 2 elements, it can be 2 different elements or the same element, but you're going to have something that is being oxidized and something that is reduced. You cannot have an element that's oxidized without having an element that is reduced. And the reason why is if something loses an electron, something else has to gain it. You can't just lose an electron and go into the ether. An element is going to have to gain it.
Reduction is the gain of electrons, while oxidation is the loss of electrons. And a very easy way of memorizing that is by simply saying oil rig. Oxidation is loss, reduction is gain. And so if you think about it, we're talking about electrons. If an element is oxidized, meaning it loses electrons, its charge is going to become more positive. If an element is reduced, meaning it gains electrons, that means its charge is going to be more negative.
So for redox reactions, let's actually look at these. So the way that you figure out what is being reduced and what is being oxidized in this reaction is you first have to determine the oxidation numbers, which we just talked about. So I have Ci4. So first of all, I'm going to look at iodine. I know that iodine is going to have a -1 charge because it is more electronegative than carbon. So that it's going to take the -1 charge. Carbon, if you notice, in order for Ci4 to have no overall charge, since I have 4 iodines, that gives an overall charge of -4. So the oxidation number of carbon needs to be +4. Okay? Br2 is by itself. so it's going to have an oxidation number of 0. For CBr4, bromine is going to be -1, carbon is going to be +4. And finally, for I2, it's by itself, so it's going to have an oxidation number of 0. So if you notice, Br goes from an oxidation number of 0 to -1. So if it's going from 0 to -1, remember electrons are negatively charged, so that means that bromine is gaining an electron, so it is being reduced, oil rig. Meanwhile, iodine is going from -1 to 0, so it is being oxidized. Okay? So keep in mind oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So in order for something to be oxidized, something else has to be reduced. So here it's Br and I, bromine and iodine. Okay? Let's look at another example. Hydrogen peroxide and reacts to produce water and oxygen. So here, keep in mind the reason why I included this, two things. This problem's a little weird. First of all, this is the one exception for oxygen when it will have not a -2 charge. So here, because it is a peroxide, oxygen will have a -1 oxidation number. Hydrogen is +1. Then for water, oxygen goes back to the -2. So hydrogen, so that the water will have no overall charge, must be +1 since I have 2 hydrogens. Okay? And then oxygen is by itself, so its oxidation number is going to be 0. So here is the weird thing. Oxygen goes from a -1 oxidation number to a -2 and to 0. Okay, -1 to -2 represents a gaining of electrons, so that is reduction. -1 to 0 is losing electrons, which is oxidation. So oxygen is both oxidized and reduced, and that can happen. It's kind of weird, but it can happen.